Hello, welcome to Deterministic Optimization. My name is Shabir Ahmed. I'm one of the co-instructors of this course. We're in the module talking about unconstrained optimization when the function is differentiable. Today's lesson is about gradient descent. So our learning objectives are to examine and understand the gradient descent method. Let's get started. Just to remind you that we're talking about an unconstrained minimization problem. So we're trying to minimize a function which is continuous and twice differentiable. And we have talked about, in the first lesson, we have talked about optimality conditions, and now today's lesson is going to be talking about the gradient descent method. Let's get started. So remember that we have talked about this general idea of an algorithm for solving optimization problems. So this descent idea. So the idea is to first start from an initial solution x0, then choose a descent direction. And we'll talk about what we mean by this. But so a direction to move in, then we pick a step size, and then we update the solution. The new point is going to be x1, which is x0, the old point, plus alpha. Here, alpha is a scalar. That's a step size, which is non-negative. So we have to say that this is non-negative, scalar. And we move along the direction of along the direction d naught, right? So this is a vector. And we keep repeating this loop until some stopping criteria is met. So now the important question is, what should be the direction that we move in, and how should we pick the step size? So let's try to understand this. Let's derive this gradient descent method. So suppose we are at a point, xk, that is the current iterate. This is a given vector. And we want to choose a direction, a downhill direction, right? And a step size alpha, such that the function value at the new point, remember, we are going to move from xk to xk plus alpha dk. The function value at the new point is less than the function value at the current point. So our step size and our direction should satisfy this inequality, right? If it does, only then we are going to improve our objective function value. All right? So let's try to understand how we can get this to hold by looking at the first order Taylor's expansion of the function at the new point around the current point. Remember that what the first order Taylor's expansion is. The function value at the new point is equal to the function value at the current point plus alpha times the gradient scalar product with the difference between the new point and the old point. Right? That's dk, alpha dk. Okay? Since we want that the new point should have a smaller function value than the old point, then we must ensure that this term is less than 0, right? Now, alpha is a positive step length. So what that means is essentially that the gradient vector transposed with dk must be negative. Now, of course, what is the best choice of dk then? So basically, I have to choose a vector. So if this is the gradient vector, I have to choose. So this is the gradient vector at xk. I have to choose a direction to move in which makes an obtuse angle, right? So we have to make an obtuse angle. So if this is the gradient vector, remember what the gradient vector means, that the function increases along that direction. That's the gradient vector. So we have to move along a direction dk such that the function is actually decreases. So if I choose dk such as this, then this angle between this is obtuse. Therefore, the scalar product is going to be negative. Now, what is the best choice of dk is obviously to move in the direction which is opposite to the gradient, right? So this is the steepest descent direction. This is our choice of direction is move in the direction which is negative to the gradient vector. So that is called the steepest descent and the gradient descent method. Good. So this is the idea. So we are going to start from the point xk. Then we are going to, and our direction is going to be the negative of the gradient direction evaluated at xk. And now we have to compute how much should we move along that direction. So there are two ways of doing this. The first is called line search. So what is the idea of line search? Is that, okay, so let me define a new function g of alpha, which is basically parameterized with respect to alpha. So which is the function value evaluated at xk plus alpha dk. Remember that xk is given to us. We have already picked what dk should be. So this is essentially the only thing that is unknown is alpha. So we'd like to move to minimize, so it's a function of alpha. We'd like to pick a step size alpha to minimize this function g of alpha. Now this turns out to be a function of a single variable. So you can use, for example, just write down the first order optimality conditions to minimize alpha. Or you can use some other methods to find it. Another way of coming up with a step size is basically just to fix a rule a priori. Just fix alpha a priori, that we're going to always take a same step size in every step. Or you could basically reduce the step size as you go along. Of course, then the algorithm may not converge if alpha is too big, if you take too long step sizes. And you're going to keep doing this. This new iterate xk plus 1 is going to be the old iterate xk minus alpha times the gradient. Remember, we're moving in the negative of the gradient direction. That's where this negative term comes in. And we're going to continue doing this until the gradient vanishes. And this algorithm is going to converge to a stationary point, right? So where basically the gradient vanishes or gets close, small enough. So here instead of the gradient vanishing, we just check when the gradient is small enough, less than some small number epsilon. Okay, so let's do a small example. So here we are trying to minimize, again, a function of two variables, x1 plus 1 to the power 4, plus x1 and x2, plus x2 plus 1 to the power 4. And we'd like to minimize this function, and we start from the point 0, 1. Right? So remember, there are two coordinates, x1 and x2, so that's the 0, 1 vector, 0, 1. The function value, you can just plug in those things. At the current point is 17. Now, what is the gradient vector? What is the gradient vector for this thing? So we have to take the derivatives. So remember, the gradient, is the partial derivative with respect to x1, and then the partial derivative with respect to x2. Right? So if you take the partial derivative of this term with respect to x1, what do we get? So we're going to get, the first term is, I'm running out of space, I'll do it here. The first term is 4x1 plus 1 cubed plus x2, and there is no second term because this does not have an x1 term. And the second term is x1 plus 4x2 plus 1 cubed. And then we plug in the values 0 and 1 here. x1 is 0, right? So I get a 4 plus x2 is 1. So 4 plus 1 is 5. That's where this 5 comes in. The second term here is x1 is 0. x2 is 1. So I get 2 plus 1 is 3. 3 to the power. So let's see. Sorry, x1 is 1, so I get x1 is 1, 2, so 2 to the power 3 is 8, 4 times 8 is 32. That's why this 32 comes in. So you get 5 and 32. These are your gradient vector calculated at the current point. So our new point, x1, is going to be the old point, which was 0, minus something alpha, whatever the step size is, times 5 and 32, right? And that's where this thing comes in. So now we'd like to find out what alpha should be. And so now we plug in the function value. Remember we write down the function as x0 minus alpha times the gradient at x0. We know what x0 is. We have just computed the gradient. If you plug in all of these things, this is what the function looks like. This function is a function of a single variable alpha. We can just take the derivative, set the derivative equals to 0, solve for it, and you'll get that alpha is equals to 0.0527. Okay? And now we plug in, so then the new point becomes this, and the function value at the new point is 0.484, which is smaller than the old function value, which was 17. So we have reduced the function value, and we're going to repeat this step. Good? So this is an example of gradient descent. So how does the gradient descent algorithm behave? So now if you notice that when we are trying to minimize the function, so at any point xk, where the gradient is not 0, the gradient descent produces the most rapid convergence locally, right? Because it is moving in the direction of the steepest descent. So the initial progress is good, but as we get closer and closer to a stationary point, remember where this gradient vanishes, because we are moving along taking steps along the gradient direction and the gradient is vanishing, the algorithm slows down, so the convergence behavior is bad. Then there is this other notion which is called the zigzagging. So let me illustrate this by a simple example. So here is our function, right? So these are the function, the objective function values. These are the contour lines of the objective function. And so suppose we are starting at this point. Suppose we are starting at this point. Now remember, the gradient direction is going to be the direction in which the function increases the most. So basically this is going to be a tangent to the, this is going to be normal to the tangent at this point. And what is our goal? We kind of move negative to the gradient. So we're going to move along this direction. And it turns out once you do that, if you look at this, the function, so remember the function value is the smallest here. This is the minimum point that we're trying to, and it increases as we go out. And now we're going to move along this direction and move until we minimize the function value along this direction. So what is the minimum value? For example, it's going to be here somewhere, right? The function value is high, it gets lower, then it's the same value here and gets higher, so somewhere around here it's going to be minimum. And now once we look at the function value here, again, what is the gradient direction? Well, the gradient direction turns out to be, the gradient direction at this point is here, and so we're going to move opposite to the gradient, which is in this direction. Right? So this is the direction we're going to move in. And again, we try to move until the function value gets smaller and smaller, and then it goes back higher, so the new point is going to be here, and we keep repeating. So you notice what is happening here is that our moves, we moved along this point, then we made a kind of a left turn, we move, and again we're going to make a right turn, and so on. So we have these 90-degree moves in these things. So this is called a zigzagging effect. So essentially the algorithms, the points that you kind of trace out look like this, right? So they look like this. So this zigzagging is kind of a bad kind of convergence behavior, because if you wanted to move from this point to that point, if there was a way to move kind of directly, that would give you a better convergence behavior. So this part just try to explain kind of more algebraically this intuitive result. So this zigzagging behavior is a problem, but that's a phenomenon of the steepest descent method or the gradient descent method. And again, so what ends up happening is you take very small step sizes near a stationary point. So those are kind of two issues with kind of the gradient descent method. All right, so let's summarize. So the gradient descent method, which it is one of the most common optimization methods, it moves from one iteration to the next by moving along the negative of the gradient direction in order to minimize the function. So we compute the gradient, we move along the negative of the gradient direction, and we have to compute a step size. Either we do a line search, or basically we solve a one-dimensional problem to find out the step size, or we can fix a rule for the step size ahead of time. Either way, this algorithm is very simple to implement and is widely used for minimizing differentiable functions. All right, see you in the next lecture.